Okay, so let's look at quiz 18.3, Gibbs energy and equilibrium. Here we have a reaction nitrogen plus oxygen in equilibrium with nitrogen monoxide. We're given a value of the standard Gibbs entropy of reaction, and we're meant to find the Gibbs energy under non-standard conditions with pressures given for nitrogen, oxygen, and nitrogen monoxide. So first we need to have an expression for Q. Q is going to equal the concentration of nitrogen monoxide squared over the concentration for nitrogen and oxygen. And in this case that would be 3.5 squared over 0.25 times 0.1. Or in other words, 490. Okay, and those pressures, as long as they're all in atmospheres, that'll be fine. The Q, the reaction quotient itself, is actually unitless. And so now that we have Q, we can use the equation that delta G is equal to delta G naught plus RT ln of Q. And so delta G, our Gibbs energy under these non-standard conditions, is going to equal that standard Gibbs energy of reaction, 175.2 kilojoules per mole, plus value of R. Here we want to use 8.314 joules per mole Kelvin, but because we're combining it with the kilojoules here, I'm going to do 0.008314 kilojoules per mole Kelvin times the temperature of 298.15 Kelvin. Times the natural log of the reaction quotient, 490. So times natural log of 490. So you can put all of that in your calculator and then add 175.2 to it in the end, and that's going to give you 190.6 kilojoules per mole. If we wanted to find the equilibrium constant for this reaction, then we'll use that equation delta G equals delta G naught plus RT ln of Q. Well, under equilibrium conditions, delta G would be equal to 0, Q would be equal to K, and we can really summarize this as K is equal to E raised to the power of the negative delta G naught over RT. So in our case, that's going to equal E raised to the power of a negative 175.2 kilojoules per mole over again 0.008314 kilojoules per mole Kelvin times the 298.15 Kelvin. And this is going to give us an equilibrium constant of 2.02 times 10 to the negative 31st. And given such a positive delta G naught, then a very, very small equilibrium constant makes sense. This is a very highly reactant favored reaction. Okay, let me scroll down to question number 2. So here we have the reaction of that nitrogen monoxide recombining with oxygen to form nitrogen dioxide. And we're given a value for its equilibrium constant K equal to 6.4 times 10 to the 9th. Can we find delta G naught for this reaction? So delta G naught is equal to negative RT times the natural log of K. So this is pretty straightforward. That's going to be, again, the negative 0.008314 kilojoules per mole Kelvin times the temperature of 298.15 Kelvin times the natural log of that equilibrium constant, 6.4 times 10 to the negative 9. And that's all going to equal, in the end, negative 56.0 kilojoules per mole. Here we have a very large equilibrium constant. It's a very highly product-favored reaction, and so we would expect delta G naught to be negative. And then finally, finding the value of Q for the reaction when we have a given Gibbs energy. So we have delta G is equal to delta G naught plus RT ln of Q. Sorry, let me scroll down to that second half of the question here. And so we can just begin to plug things in here. We have 3.14 kilojoules per mole is equal to negative 56.0 kilojoules per mole plus 0.008314 kilojoules per mole Kelvin times 298.15 Kelvin times the natural log of Q. I almost ran off the screen there. You can solve this perhaps most easily in 2 steps. So we'll have the natural log of Q is equal to 23.86. And that means that Q is going to equal E raised to the 23.86 power, which is going to be equal to 2.30 times 10 to the 10th. So that is quiz 18.3.